Hi guys, so my name is Vinay Jain and today I wanted to talk about breadth first search algorithm in a general tree instead of in a binary tree like we've discussed earlier in earlier videos. So what is the difference between a general tree and a binary tree? Binary tree is which in every node consists of not more than two child nodes. So let's say this is one node and then it has two children, 2 3. Then this node 2 has one children and node 3 has two children, 5 and 6. So this qualifies for a binary tree because it doesn't have more than two children nodes. On the other hand, the diagram that we have on the left hand side, this depicts a general tree where it can, like, any node can have one children, two children, or more than that. So for example, let's say we consider the node B. We can see that if we start from node B, it has three children, A, C and D. If we start from node C, we have A as its child, B as its child, D as its child, F as its child. So there are four children for it. So how do we work in such scenario? How does the breadth first search algorithm work in this type of tree? So the idea is very similar. So let me show you it via a dry run of this algorithm for general tree. I also wanted to take this time to explain why are we using visited set in our breadth first search algorithm. What is the purpose of it? So we're going to be discussing that in this video. So as breadth first search algorithm begins, we're going to add root of the tree to the queue, and now we're also going to add it to the visited set, signifying that we have already visited the root node, and therefore we added to the visited set. Now that we've done that, again, what was the purpose of visited set? To keep track of all the nodes that have been visited so that you do not again traverse them. So this is the purpose of the visited set. So now we begin our breadth first search algorithm. We pop the topmost node in the queue, which is node A, add it to the pop node. Whatever its children are, then we add it to the queue. How many children does A have? It has two children, right? So we add those to the queue, B and C, in whatever order you want. So let's say I added in this order, and now we add B and C to the visited set. Notice we're adding earlier this time. Instead of adding at the last after exploring each individual node, we're adding the children nodes in the beginning, in the early stage. So now that we've done this, we again pop whatever is at the top of the queue, which is node B, assign it to pop node, check for its children. So node B has, what all children does it have? It has A. Let's say A is linked to it. A is its child. If we start from B, C is its child. If we start from B, D is also its child, right? So we check all these children. So we are supposed to add all these children to the queue, but note that A has already been visited and it's already in the visited set. C has already been visited as it is already in the visited set. So we do not need to add these in the queue again. We just need to add the node D. So that is what we do. We just add the node D in here. We don't add A and B because A and C because they have already been visited and they are already in the visited set. So that is the purpose of this visited set, to make sure that we do not again add those into the queue and traverse those nodes again. So now that we've done this, we've explored node B and it is in the visited set. Whatever the childrens we have added for the node B, we add them as well to the visited set. So node D is added to the visited set. So next we again pop whatever is at the top of the queue, that is node C, assign it to the pop node, check for its children. Its node C children are A, B, D and F, right? It has four children. So how many of its children, node C's children, have already been visited? So A has already been visited, B has already been visited, D has already been visited. It's just the F node that has not been visited. So we only add the F node in the queue then, because rest all have already been visited, and we add this as well to the visited set to keep track of what all nodes have we explored so far. Now we next pop whatever is at the top of the queue, which is node D. Node D is assigned to the pop node. Check its children. Its children are B, C and E. How many of them have already been visited? B has been visited, C has been visited, E has not been visited. So we add E to the visited set as well as to the queue, right? So now that we have done this, we then proceed as usual, which is pop the next node in the next topmost node in the queue, which is node F, and assign it to the pop node. So what are the children of F? F has two children, G and C, right? So out of these two children nodes, which all have already been visited, C has already been visited, right? You can see that here, and G hasn't been visited. So we only add G to the queue. This is G, yeah, and we also add it to the visited set, signifying that we've worked with this node. Now that we've done this, we again then pop the next topmost queue, which is node E, and assign it to the pop node. Node E has how many children? It has two children, which are D and G, right? D and G. Which of these two children nodes of E have already been visited? D has been visited, G has already been visited. So we do not need to do anything since all his children have been visited. We do nothing and we add nothing to the queue. Next, what we do is we pop the next topmost element in the queue, which is node G. We pop this, assign it to the pop node. Now, what are the children of node G? Node G has two children, E and F, right? So out of these two children, which has not been visited and which has been visited, both have been visited. So we do not need to add anything to the queue, and we do not need to add anything to the visited set. So this concludes our breadth first search algorithm for a general tree in which every node can have one children or more than one. That means 2, 3, 4, any number of children. And this is the order of the visitation of all the nodes in the tree. First A was visited, then B was visited, then C was visited, then D, then F, then E, and then G. So this is the breadth first search traversal, or you can just say breadth first traversal of this tree. At any point of time, if you would have been looking for a target node, at any point of time in this iteration, whenever the pop node would have matched the target node, then you would have returned it. The idea is the same as the original breadth first search algorithm. So I hope you understood the purpose of this visited set, why we use it, and how it is helpful when we're working with general tree and using breadth first search traversal in a general tree's case. So what exactly is the algorithm for this case, for working with a general tree and we're doing breadth first search in it? So the algorithm for this is somewhat like this, where the first step is, as usual, add root node to the visited set and empty queue. You just add that to the visited set as well as the empty queue. When you're done with that, while queue is not empty, there is a node to be worked with in the queue. So pop that node and assign it to pop node. Pop the topmost node from the queue and assign it to pop node. If the pop node's value is equal to target, that means you have found the node which you were looking for. So you return true. That means you found the node that you were looking for. If not, then you move ahead, and for all the children nodes of pop node, whatever the current node you're working with, whatever the children nodes are, how many they are. So for every single one of them, you check if they are not in the visited set. If they are in the visited set, that means you have already worked with them and you do not need to work with them anymore. And you do not need to add into the queue. If they are not in the visited set, that means you need to work with them and therefore you add them later into the queue as well as in the visited set, so that the next iterations know that this node has now been visited. So you keep on working with this until and unless you iterate over all the nodes in the queue or you find your target. When you have iterated all the nodes in the queue and you still not get anything, then you exit the loop at this second point and you come to the third point. That means you still not found the node that you were looking for, right? So the queue is empty now. and therefore you return false because there are no more no more nodes to be searched for, and your node that you were looking for actually doesn't exist in the tree, and therefore you return false. So the time complexity of this algorithm is also OV plus E, and the space complexity, this is time complexity, and the space complexity is O of V, again where V is the number of vertices, E is the number of edges. So thank you for watching this video. I hope this helped clear your concepts. Have a nice day, guys.